All right, so in this video, we are going to do the efficient market hypothesis, but this time we're going to actually do it in Python. So just to kind of review what the efficient market hypothesis is, it states that returns in the prior week, so we're going to deal with weekly returns, and returns in prior weeks should not help predict return in future weeks. So with this, we're saying that the expected value of return t, given historical returns, is still going to be the expected value of RT. It doesn't change it. So the expected value of our return at time t does not depend on previous returns. If this is false, then it violates the efficient market hypothesis. So for this, we're going to do a strict form, a very strict form of this. We're going to do where the alternative hypothesis is going to be a first order autoregressive model. So for an first order autoregressive model, we're saying we'll have beta 0 plus beta 1 times previous week. So if the null hypothesis is that if the efficient market hypothesis is correct, that means beta 1 is going to be equal to 0. If it's not correct, then beta 1 is not equal to 0, and we can use historical returns to predict future returns. So now we'll do this in Python. So I'm going to go to our Jupyter notebook. Let me make it bigger. I'm going to zoom in. All right, so in order to do this, it's pretty simple. We're going to import NumPy first. We're going to import NumPy as NP, import pandas as PD. We're going to import statsmodels.api as SM for stats models. And let's import pyplot, matplotlib, import pyplot as PLT. Do the magic command. Let's import Seaborn too, depending on what we want to do. And we'll do the magic command so we can see matplotlib plots in our notebook. Let's set the Seaborn style to dark grid. All right, so now on eCampus you have the CSV file for the New York Stock Exchange. So we're going to read the CSV file. So whenever we do this, our file path will be the CSV file. I took this from Yahoo Finance. We're going to set the index column equal to date. Whenever we do this, we're going to get the following data frame. And whenever we get this, we only want the prices. We only want the adjusted close. So we get our adjusted close, and let's from there now let's calculate our stock return. We're going to do log return. To do a log return, there's two ways to do it. You could do numpy.log stock prices dot percent change plus 1. This would give you a log return, or you could do the difference between log prices. So stock prices, natural log stock prices minus natural log shift 1. Both of these will give you the same output. So we did it. Let's look at let's do .describe to look at the summary statistics. We get this. So now before we even do anything, let's plot our stock return. Let's just do a simple plot. This is consistent with what it should look like. This would be I think this goes from 2020 or 2000 to 2015. So this this large spike in volatility would be probably the Great Recession. You don't see the date down there. I'm not sure why that's coming up, but that's not important for right now. So whenever we do this, we'll assume that all the assumptions from last video work out. So we can just use ordinary least squares to calculate it. So let's trade a blank data frame, and let's trade a column for YT, which will just be our stock returns. Stock return column. Then let's trade another column. We'll say Y of T minus 1. So it'll be one lag. This is going to be our stock return shift 1. So it's going to be one behind it. After we do that, let's look at the first few rows to make sure it worked, and it did. Now, in order to do a in order to use stats models, or in order to use really anything from stats models, it can't have nands in it. It can't have knotted numbers, so we'll have to drop those. The first two should be the only ones that are there. So let's drop our nands. We do this, and didn't save it in place. We want it. The default is in place equal false. We want to do in place equal true, so it keeps it in place of the original data frame. Now we can run our regression. So we'll set our regression equal to stats models dot ordinary least squares. Then when you shift tab, you see the our y endogenous. You can just do a y. You don't have to name the parameters if it is in the correct order, but we'll name it here just because. And the exogenous exog will be our lag. But in this, in order to do ordinary least squares, you have to add a you have to do the add constant. So you can either manually do it yourself, or we just tell it to do it for us. Either one will work. It'll give you the same value. So this is going to be our lag of 1. We're going to fit it, and let's print the summary results. And we get the same I believe the same values from our previous video. Yes, so these are the same values from our previous video. So our t statistic is again our coefficient, our beta 0 coefficient, 654, divided by our standard error of our beta 1, and we get a t statistic of negative 1.89. And given a 5% significance level, we failed to reject the null hypothesis. So this we failed to reject the null hypothesis. So this means that the efficient market hypothesis still holds. So this does not violate the efficient market hypothesis, and everything checks out. So this is this was the efficient market hypothesis. In the next video, we'll cover an ARMA model, so an autoregressive moving average, where we combine the two univariate time series models.